good morning everyone. Thank you all for being here. As Wendy said, my name is Adi and I'm an incoming second year electrical engineering student here at UCSB. So this summer I'm conducting research through the AIM Photonics program, and I'm working under the guidance of my mentor Takako Hirokawa and faculty advisor Professor Glenn Scow. So my project is simulating a Mach-Zehnder silicon photonic switch. So everyone has heard the term electronics before, but not a lot of people know what photonics is. So broadly speaking, photonics is the study and application of light. Light could be visible light, it could be infrared light, but the fundamental particle of light is the photon. With electronics, however, you're studying the flow and control of electricity, in which case the fundamental particle is the electron. So everyone has heard the term fiber optics before. And optical fibers are mediums that are made out of glass or plastic, which transfer information using light. And what we have in our houses are coaxial copper cables, which can be used for things such as television, cable, internet, and various other purposes. So optical fibers do offer several advantages over traditional coaxial cables. First one being speed, in that photons do not have mass, whereas electrons do have mass. And there's more resistance involved when you take into account just the distance that the information has to travel and all the electrons in the middle. The second advantage is the bandwidth. And this is referring to the range of frequencies along which information can be transmitted along a single strand of optical fiber compared to traditional copper cables. And this is done using a technology called wavelength division multiplexing, which allows you to send signals using various optical frequencies. You also have low attenuation, meaning low signal loss over longer distances. More immunity against electromagnetic interference, more durability because there isn't that level of heat in comparison to copper cables. There's almost no heat produced in optical fibers, and there's security because it's really difficult to tap into optical fibers, and if someone is able to, then you know that there's a leak in your photonic system. So optical fibers are in many ways better than copper cables, which is why they're used in data centers. And recently, data center traffic or data traffic has increased a lot and is expected to increase almost 5-fold in just 4 years. And as a result, data centers continue to grow in size and in complexity. So a device that is used to make it easier for us to manage the flow of information within data centers, as well as just to help negotiate the physical and virtual resources, is a photonic switch. And this is a device that helps reroute information transmitted at different optical frequencies. So here's a black box of what a photonics 4x4 switch is, which just means 4 inputs and 4 outputs. And each of the colors here represents a certain optical frequency at which information is being transmitted. So my project is to determine the bandwidth, which is the range of frequencies that can be switched. And here we have a layout of a small portion of the switch. These here represent the waveguides, and this device here is a Mach-Zehnder interferometer. All 3 of these are interferometers, which is why the switch is called a Mach-Zehnder photonic switch. So apart from determining the bandwidth, I also simulated the loss. And if the switch isn't optimal, I will find ways to increase the efficiency, reduce the crosstalk, which is the unwanted transmission into another port, or also reduce the footprint of the device. So the first step is to do performance checks. And these are just sanity checks to make sure that the waveguides and all the different components of the switch are working optimally at the intended frequency, which in this case was 1310 nanometers. So here you just set up the silicon waveguide. You have a light source of a certain wavelength or frequency. You have the monitors, and then once you run the simulation using numerical FDTD, you can get a graph that looks like that. And here, this is showing the intensity of the electric field as the light propagates along the waveguide. And as you can see, there's not much loss at 1310 nanometers. So the next step is to calculate the parameters. So here I have to find the different aspects of each component of the switch, and these include the effective refractive index, group index, loss, and dispersion. Now I'll just take a step back to say that the switch was designed by my mentor, but before it was sent out for fabrication, we didn't know any of its characteristics, so what frequencies can be switched, and that's what I'm doing. So the different components of the switch include things like, well, directional couplers, 90-degree bends, S-bends, and discrete waveguides. And to give you an idea of what each of those look like, this here is the directional coupler. This is the U-bend, or two 90-degree bends. And this here is the S-bend. And you can see these orange lines. They represent the eigenmode solvers, which help determine the modes and all of these characteristics that you're looking for. So the final step is to actually determine the bandwidth by using the parameters that I gained in the earlier step, and then setting up a model of the switch in numerical interconnect. And this is my model. Well, this is the photonic switch, and then this entire thing is the test setup. And I hook the photonic switch up to a pseudo-random bit sequence generator, and you also set up a laser, and then you use eye diagrams and bit error rate testing to see how well the switch is performing at a certain optical frequency. So in our case, the bandwidth is determined to be the cutoff threshold of 10 to the negative 9. So what that means is you cannot have a bit error rate that is higher than 10 to the negative 9. Otherwise, that is not considered to be part of the bandwidth. So these are just some of the results from the waveguide parameter calculations. And so the refractive index of silicon is 3.44, silica is 1.43, and from these you can see that the effective index depends on the refractive indices of these, because these are the materials that were used in the setting up of the switch, and it was determined to be approximately 2.22. So these numbers might not mean much to you. Overall, the calculated parameters do seem most likely accurate, although the loss does seem slightly high through the 90-degree bends as well as through the straight waveguides, which is obviously not a good thing. Now, I mentioned an eye diagram before, and this is what an eye diagram looks like. So, as you can see, the curves are, well, really nice, and there's not much jitter, meaning that it doesn't look unstable. The line you can see on the top is pretty much straight, and it's not extremely thick. So this diagram is just a superimposed series of graphs of ones and zeros. And this would be the ideal case scenario if you were to use an eye diagram to test the performance of the switch. This is not something that you would get, that is impossible, but this is something that you should aim for. And the bit error rate should be much less than 10 to the negative 9. For an eye diagram like this, I believe it's 10 to the negative 300, which is extremely low and impossible to achieve with a photonic switch. Now, this is the actual result from running the simulation through just one of the components of the switch. And as you can see, the difference between this diagram and this diagram is huge. And now you know what I mean by the thickness of the one mark. And the bit error rate was determined to be 0.024, which is incredibly high, much higher than 10 to the negative 9. So what this suggests is either the parameters calculated are incorrect, and that's a higher possibility than the second alternative, which is that the photonic switch was designed poorly. So this is where I'm at right now, and there's several parameters to calculate, which is why there's a lot of room for error when you're determining these things. So my future goal is to continue trying to determine the bandwidth of the switch, mainly because there's always the possibility that there was the one parameter that was incorrect because of some unusual reason. But by determining the bandwidth of the switch, we can then develop test cases for the switch once it actually arrives from fabrication. And if it does turn out that the switch wasn't developed or designed properly, then I can find ways to reduce or increase efficiency as well as reduce the crosstalk of the switch. So after 8 weeks of this program, I'm convinced that photonics is the future, and this is a quote that I thought summed it all up, is that the 21st century will depend as much on photonics as the 20th century depended on electronics. So I'd like to thank my mentor, Dr. Ko, for answering all my questions and guiding me throughout this process. Professor Clint Scow, Akilish, who's a grad student in Dr. Bauer's lab, and then Wendy and Jens for helping us out with the non-scientific personal skills throughout this process. Thank you.